Assalamualaikum warahmatullahi wabarakatuh and good day. So today we continue back our 1.2 commonly used discrete probability distribution with the Poisson probability distribution. So from previous video you have learned the hypergeometric probability distribution function, geometric distribution function, binomial, and then you have learned also negative binomial. Okay, you have learned 4. Okay, binomial, geometric, negative binomial, hypergeometric. So now this is the last one, is Poisson probability distribution. So how do you know it's a Poisson distribution function? When you want to know the number of certain things at a particular intersection during a time period of a certain time. For example, number of accident per week or number of people cycling per month. So within a time, within per month tu, you want to see how many participant. Okay. Okay, if you look book now, okay, suppose we want to find probability distribution of the number of automobile accident at a particular intersection during a time period of 1 week. So at first glance, okay, this random variable, the number of accident may not seem even remotely related to a binomial random variable, isn't it? Binomial, you must have two outcomes, okay? Yes or no, true or false, okay? But we will see that there is an interesting relationship exists, okay? So now think of the time period, 1 week, this example, as being split into n sub-interval, each of which is so small that at most one accident could occur in it with probability different from 0. Alright, so you can see we can denote like these three things here. Okay, first, okay, the probability of an accident in any sub-interval by P. So we have probability no accident occur in a sub-interval. So we will have 1 minus P. Because P is what? Number of accident. Okay, the probability of accident happen, which is P. So if no accident happen in the interval, 1 minus P. Okay, if one accident occurs in the sub-interval, so within the interval, one accident, we will have P. So if more than one accident occurs in a sub-interval, we will have 0. Okay. So basically, okay, the total number of accident in a week is just the total number of sub-interval that contain one accident. Okay, so if the occurrence of accident can be regarded as independent from interval to interval, the total number of accident has a binomial distribution. Okay, either accident or not, either accident or not. So you have two outcomes. Okay, so there is no unique way to choose the sub-interval. Okay, because let's say 1 week though. So within 1 second to 1 second is an interval. From 1 minute to 1 minute is interval until 1 week, isn't it? So we didn't know. There is no unique way how to choose the sub-interval. So therefore, neither n nor p. Okay, so it seems reasonable that we divide the week into a greater number of n. Okay, because we have 7 weeks. We have 1 week, we have 7 days. So first day until 7 days. Okay, but within these 7 days, there is a sub-interval. Okay, 1 minute, 1 second, 1 hour, okay, 1 day, and so on. So we didn't know how many to divide. So this is called n. And then P is the probability one accident happen. So that's why we let lambda equal to NP. That means number of accident times, number of interval times the probability of one accident happen. Okay, so that's why we let lambda equal to NP. And then by taking the limit of binomial, so we have this one, okay, if you remember, this is binomial. And as n goes to infinity, okay, you will get this equation. Okay, so finally, okay, all other term to be right up to the limit have a limit of 1, we will obtain this probability. So basically, if you look here, we have limit to the left and to the right. Okay, so this is probability and this is binomial lah, if you remember. Okay, but we give limit from n goes to infinity, and the other side as well, we break the apa ni, the bracket ni, so we will have like this. Okay, and then P ni become alpha over n lah, because from here, isn't it? From here is lambda equal to n over P. So here is P. P will be lambda, lambda equal to np. So we want P, isn't it? P equal to lambda over n. Okay, so that's why when you substitute here, the P tu, you get lambda over n, and here is 1 minus lambda over n. Power similar lah, n minus 1, y. And then we give the limit n goes to infinity, and then here if you look, we factorize lambda y over y factorial. Okay, and then you can see we finally have 1 over lambda over n power n, and this one you will get n, okay, ny, because you want to apa ni, because you have factorized just now lah, and then here suppose y factorial, isn't it? But you have here, so it become n power y, and then here from you have here n, so here will be negative y lah, power negative y, here is n, so this is actually n minus y. Okay, and then you bring out lambda power y factorial, because we don't have n here, so you can bring it out, and then here you have n, so remain. This one you also have n, so remain. So this one, if you look this one, okay, here they break it into 1 minus 1 over n. Okay, and then you also have 1 minus 2 over n times until y 1 minus 1 minus 1 over n. Okay, so this is how you break it. Okay, this one you must look carefully how is it. Okay, but this is the factorized lah. All right, so then after you look this equation, you note that this one actually you can have 1 over lambda over n power n, because you have power n negative y, and then you have power 1 power 1. Okay, and this one actually is exponent power negative lambda. Okay, so that's why when you have this one, all this from here to here is negative power lambda, so this one will be put back here, so here will be this one. So that's why you get the probability of Poisson distribution function. Okay, whereas your y is the number of accident per week. So in this case, we are consider per week. So it also generalized to any interval, per apa ni, per month ke, per year ke, okay, per apa ni, biennial ke, okay, setiap 2 tahun ke, and so on. Alright. So that is Poisson distribution function, and then your y is from 0, 1, 2 until infinity, and then your lambda should be greater than 0. Okay, now we move to the example here. Okay, so if you look at example 3.18, this one. Okay, show that the probability assigned by the Poisson probability distribution satisfied the requirement that P is between 0 and 1 and for all y, and summation ypy is equal with 1. Okay, so this one should be summation of ypy ni. Oh, betul lah, summation py equal to 1. Okay, where y from 0 until infinity. Alright, so since lambda greater than 0, so it is obvious to show that the probability of the function is greater than 0 as well, because your y is start from 0, 1, 2 until infinity. And then the other way around, and probability y equal to 0 otherwise. Okay, so if you look here further, okay, at the first place, if you do it, okay, properly, so you will have like this lah. Okay, summation of py, okay, this is y from 0 until infinity. Okay, so what is your py? Py previously is your probability density function, probability mass function. So you will get py, I think I put something here, insert new slide. Okay, I try to do this. Okay, so actually you have summation y from 0 until infinity py. So this one actually summation y equal to 0 infinity. So py is this one. Okay, so you will have lambda y factorial e lambda. Okay, so this one you can see, you can bring out, what is it? You can bring out this one lah, because you don't have any y here kan. So e negative lambda summation y from 0 until infinity lambda power y over y factorial. Okay, now this one, what is it, this one actually? So this one is also exponent power lambda. Okay, this is by theorem. So this one, if you met, you get 1. So proof. Alright. You must remember this one. Infinite sum of this one is a series of exponential power lambda. This one. Okay, this one you learned before. Okay, so that shows you how is it. Alright. You can also look here lah at appendix A1.11. You can refer back. Okay. And then theorem. Okay, so this is the theorem. Theorem 3.11. Okay, a random variable y is said to have a Poisson probability distribution function if and only if you have this one. Sorry. This is theorem 3.11 is the definition. Okay, but your theorem here is this one. What is it? This one. Okay, that's mean what is your mean here, and then what is your variance. Okay, now we are talking about population mean and population variance only. So how to prove that? Again, if you want to prove the expected value for the Poisson, which is mean, you will have like this lah, mu equal to y. So this one actually summation y py. Okay, so this one I from 1 until infinity lah in this case, because y from 0, 1, 2, 3 until infinity. So here you will get summation I from 1 until infinity y. What is your py? Your py is lambda y e exponent power lambda over y factorial. Okay, again you can bring out, what is it? Okay, you can bring out exponent e actually, but before that, if you look, if y equal to 0, okay, from the first term tu, if y equal to 0, and then you multiply with the PMF ni, you will get 0. So we need to start with 1. Okay, so when we start with 1, you will have, this one 0 sorry. So I equal to 1, here infinity. So here basically you will get y. Okay, here will be lambda power y exponent lambda y. Okay, and then if you start with y here, this one become 1 minus y minus 1. Y minus 1. Okay, factorial. Lama. Okay, so now this one we have a mistake here. Okay, when we have I from 1 to infinity, this y is no more lah. No more this y. So we only have this one. Okay, lambda y exponent negative lambda over y minus 1 factorial. So now, in order to solve this one, we use the previous lesson. Okay, whereas we can factorize lambda. Okay, when we factorize lambda, we will have y start from 1 until infinity. So here will be lambda. Okay, here will be y minus 1 as well. Okay, because we start with because we factorize lambda, so here will be y minus 1. Okay, before here we have lambda y, but we bring out 1 outside, so it become lambda y minus 1, lambda power y minus 1. And then exponent negative lambda. Here is y minus 1 factorial. And then we let z equal to y minus 1. Okay, and then you can have y equal to z plus 1. So here, because we want to make, after this one, okay, we want to make the summation here is from 0, because previously for Poisson, y is start from 0, 1, 2 until infinity, isn't it? So that's why we cannot have start with 1. So we must have start with 0. So in order to start with 0, we let z equal to y minus 1. So that's why here you will have z from 0 until infinity. But here you will have lambda z exponent negative lambda over z factorial. Okay, so you can see that this is what? This is the pz, probability z, which is equal with 1. So since this is equal to 1, so you will get lambda. So it's proof. It's a lambda. Okay. All right. So next, variance. Okay, I put here slide. Okay, so now we do for population variance for the Poisson distribution. Okay, so basically we have population variance equal to Vy. This one you will get lambda as well, isn't it? And then do you remember when we have variance, we will have this one. Ey, y minus 1. This one similar with Ey squared minus y. So this one you can have Ey squared minus Ey. Okay, and then Vy is what? Expected x square minus expected x, all is square. Okay, so here actually we will get kenapa x pula? It should be y. Okay, sorry, confused pula. This is your y. Okay, so y minus 1, and then plus y square minus all is square. Okay, all right. So now we do this one first. Okay, so here it will be y minus 1. Here you will have summation y from 0 until infinity. Instead of ypy, you will have y minus 1 py. So py ni is the PDF lah. So you will have summation y from 0 until infinity. Y minus 1. Here will be negative exponent negative lambda power y factorial. Okay, so this one you can change. Summation y equal to 0 until infinity. Y minus 1. Here will be E negative lambda power y. Here you will get y factorial, not y factorial, y y minus 1, y minus 2 factorial. Okay, so can you see y minus 1 ni you can cancel it out. So when you cancel it out, okay, you will get summation y until infinity e negative lambda lambda power y over y minus 2 factorial. So here your y is start with 2. Okay, because of this one. All right, so now we can factorize this one. Okay, we can bring out, okay, what can we do here? You can bring out exponent negative lambda summation y from 2 until infinity, and then lambda y over y minus 2 factorial. All right, so from here you can start, you can let z equal to y minus 2. All right, so now from here, okay, from here you will get exponent power lambda. Okay, here lambda y will be z plus 2, isn't it? Z plus 2 over z factorial. And then here you can start z from 0 until infinity. Okay, and then this one. Okay, so if you remember here at this part, okay, this part, okay, if you look, if you look this one actually lambda power z times lambda power 2. Alamak. I think this one could lambda power 2, lambda power z times lambda power 2. This one, okay. So basically you will have exponent e lambda, and then lambda 2 ni you don't have any z here, you can bring out outside. Then summation z from 0 until infinity lambda z over z factorial. And then if you look this one, what is it? This is lambda z. This is exponent power z. Exponent power lambda. Okay, this is exponent power lambda. Okay, this one will be exponent power lambda. Oh my god, this one, yeah. Okay, power lambda. So, negative lambda with lambda, it will be get 1. Okay, so here you will have lambda square only. Alright, so this is for this one. Okay, so you have lambda square plus this one. Remember from previous mean you get lambda, and then here you get lambda square as well. Okay, so when you get lambda square here, so here you get lambda. So this is your answer. So it's proof. Okay. So that's how you do for Poisson. Okay, for the mean and for the variance. Okay, so you can see lah. Okay, how I do it. All right. Okay, so now this is example. Okay, example about 3.22, page 135. So industrial accident occur according to a Poisson process with an average of 3 accidents per month. So you can see average. So that means mu is equal to lambda, isn't it? So lambda here 3 accidents per month. Okay, because Poisson you have value certain time, month, week, and so on. So you can see here an average of 3 accidents per month. So during the last 2 months, 10 accident occurs. Okay, the last 2 months, 10 accident occur. Does this number seem highly improbable if the mean number of accident per month? Is it impossible or not? If the mu is still equal to 3. And then, does it indicate an increase in the mean number of accident per month? Because you can see per month 3 accident, but during the last 2 months you have 10 accident. Okay, so you want to see, is it impossible or not? The mean still equal with 3. Okay, does it indicate an increase in the mean number of accident per month? Okay, so you want to check that one. So in order to check, so if you look the solution from the book, okay, this one is page 135. So you can see here, okay, the number of accident in 2 months, y. Okay, so basically y has a Poisson probability distribution with mean lambda. So lambda is 3, but that one is for per month. When we have for 2 months, okay, when we have for 2 months, so when we have for 2 months, we times 3, so you get 6. So the probability that y is as large as 10 is what? So here, we will have probability y greater than equal with 10. So here, you will have y equal to 10, and then until infinity. And then your lambda here is 6. Your y is equal to 10. Okay, so basically you can also do using per table. Okay, using your statistical table, Poisson distribution, or maybe you can use R. Okay, but from theorem 3.11, okay, theorem 3.11, which is you learned before ni, so your mu is 6, so your variance is 6. Okay, because remember, your mu equal to lambda, your variance is also equal with lambda. So before this, when for 1 month, you have lambda equal to 3. But this one, your y is for 2 months. So you get 6. That's why your variance also equal with 6. So for standard deviation, you get 2.45. So in empirical rule, okay, we should expect y to take the interval mu plus minus 2 standard deviation. Do you remember this one? This is Chebyshev theorem. Okay, so the mu should be within 2 or 3 sigma. So in this case, we consider 2 sigma. So if you substitute the value, you will get 10.6, 10.9. So this is called 10.9 months. Okay, so the observed number of accident y equal to 0 does not lie more than 2 sigma, okay, from mu. Okay, because when you have 2 sigma, it's between it's until 10.9 lah. So actually, if you do this for the other side, okay, if you do this for the other side, it will get this one 6 plus, isn't it? After this, you will have 6 minus. Okay, so let's say 2 times 2.45, 6 minus answer, you get 1.1. So the range ni actually is between 1 until 10.90. So 10 tu is still in this range, okay, close to the boundary. Okay, so that's mean does not lie more than 2 sigma. So it's not highly improbable. Okay, actually this is not highly impossible, tak mustahil. Okay, but it may be sufficiently improbable to warrant an investigation. Okay, we should investigate lah because it's near with the boundary. Okay, so this is an example. So class, for this video, very important is about Poisson distribution function. Okay, you must know how is it is a Poisson distribution function. Okay, Poisson probability distribution. Okay, when you have an average or number of something in a certain interval, and then you must remember the theorem, okay, to find the mu and then to find the variance. Okay, how you prove it. All right, and for sure, when you have example like this, application example, you must understand how to solve. So I think that's all for today. Thank you, class.